And can you hear us now? Hello? Can you hear us? Hello? 1, 2, 3, 1, 2, 3.
Yes.
Okay. So hello everyone. Welcome to yet another meeting of the informal Stark at Home, or in this case, actually, it's Stark at the Office informal webinar. It's a very special occasion and great honor to have with me three of my colleagues here at Starkware, who will later take the main part of this talk after a brief few words. I have with me here Michael Riabtsev, my co-founder and chief architect at Starkware. We have Lior Goldberg, head of algebra research, and we have Shachar Papini joining actually from home, engineer in the algebra research team. And this episode is going to be a bit more of a, I don't know, like something between deep dive and philosophical discussion about how do you convert computational problems or frameworks for dealing with computational statements into proofs in a very efficient way. And just for those who are new here, let me just remind you, there's an Ask a Question button at the bottom. And once in a while, we'll pause and see if there are questions. You can also use the chat room, but it's a bit easier to use the Ask a Question because that sort of keeps track and then we answer it. And yeah, so that's it. Without further ado, let me just formulate the kind of question that we want to deal with, and for that I'm going to share my screen so I can scribble for no real reason other than it makes me a bit more occupied with the things I'm doing. So, okay. So basically what we want to start, we have some high level specification. There's some problem that we want to argue computational integrity about. So this could be a trading system. It could be some statement about a VDF. It could be something simple like a statement about computing Fibonacci, and we have a whole bunch of problems that we would like to somehow prove statements about. We want to prove, we want to be able to move to something where we prove computational integrity statements about these things, okay? So this is very similar to the general problem of programming, where we would like to, we have all of these problems or algorithms or pseudocode in our head that we want, or smart contracts or systems that we want to implement, and then we have to sort of realize them in a way that is efficient and secure and easy to use, and we can sort of human readable and all those things. So there are a bunch of things that we would like to have at our disposal when we sort of do these things. And of course, now we have this new proof system, and we in particular work with Starks, but of course it could easily be something else, like it could be a Snark, it could be some, it could be a Plonk, it could be some Bulletproof, or any of the other systems, Fractal. All of them sort of have some weird sort of target language or domain, or the way you argue about things, and you usually start with something that is very high level or sort of looks very different. So we want to have these reductions at our hand, and we want some sort of tools that will allow us to do these reductions sort of easily meaning something like a programming language or something that is easy to write in. We would like them to be safely done, so like, you know, eliminating finding and finding bugs and removing them. We want it to be done efficiently, which in our context means small proofs or small proving time, and we want it also to be done generally, which means sort of not just for some specific program, you know, for all programs. Sometimes we talk about, you know, Turing complete or something like that. And then basically what we're going to discuss soon in a minute are like, you know, the evolution or how we've been thinking about going through three that are four different kinds of, let me just move this down a little bit, 3 or 4 different kinds of, you know, schemes for writing things. So you start with something that is the analog of A6, and you write by hand. Then you can maybe consider something like a DSL, which gives you a little bit more flexibility, and we'll discuss, you know, the pros and cons of these things. And then you go to something that is Turing complete, and here this sort of breaks up into 2 options. You can either go with Harvard, or you can go with von Neumann. And basically, I just want to say, we sort of started with this, or somewhere between, I don't know, this and this. And now the next thing we're going to do will be sort of jumping all the way to von Neumann architecture, which is Cairo. But we want to sort of share with you some of the thoughts and processes that sort of went into both the ASIC world and then to this transition. So this is my introduction. The next part, after we pause for questions, if there are any, I'm going to hand it over to Michael, who's going to explain a little bit about the thing that we use at the end here. So we want to start with high-level specifications, but we end up with something called airs. And I'm going to let Michael explain that. That's going to be the second part, and then we're going to talk about how we go through these different phases of designing, you know, dealing with universality and general computation. So now I'm going to pause and see if there are any questions, and then I'm going to hand it over to Michael. Okay, I see so far there are no questions. I don't know if you want to use the chat room, the chat, or if I'm just going to wait to see if anyone has a question about this part and the goal of this talk. Michael, you can meanwhile set up maybe. Okay, you have it. Okay, you have your own pad. Cool. Okay. Okay, so now I'm going to hand it over to Michael. Okay, go ahead. Wait, are you signed in through something different, or should I just?
No, just I'll scroll a bit.
Okay. Do you want to move a bit closer here so that you're closer to the camera and mic?
I think. Can you hear me well? Can I hear me well?
Let's see. Michael, can you say something? Let's see.
Can you hear me well? I'll come closer. Maybe I'll use your laptop here.
Okay, I'll just answer. Will Cairo be open source? So over time, yes, it will end up being open source. Yes, not all parts immediately at start, though everything that goes on-chain related to Cairo will be open source from day one, the smart contracts that go there, but and over time we'll release more and more stuff for the community. But I just want to stress, this is not a talk about Cairo, this is like sort of a talk preceding a talk about Cairo. This is about, you know, how did we end up with Cairo? I'm not reading up there.
Will any of the ASIC Stark decks be open sourced?
Will the what?
Any of the ASIC or Stark decks will be open sourced.
So I prefer to have the discussions more about you know, general intellectual problems rather than intellectual property questions, but though they are interesting. The Cairo programs that we are writing, we will put up before everything goes online, we'll put up full information about all the different licenses that go with everything. I'll just say very briefly that the smart contracts that are with Cairo, the verifier and the auxiliary stuff is open source, is going to be open source under Apache. The programs that we have written for our customers, initially for something like half a year, they will be under a time-limited license, but they will be source available. And we'll take it from there. We'll deliberate on what are the next steps. But please, let's focus on intellectual questions and less intellectual property questions. Michael, please.
Okay. Thank you very much. I'm very excited and honored to be here. I'll just move this a bit up. How do I? This way.
Yeah.
Okay, so
just make sure to just go here and let's see that that everyone sees it.
Let's focus on.
Okay.
Yes,
Go ahead.
okay. Okay. So let's talk about what is an error. I will just tell what are the acronyms first, and then we will see what they mean. So error stands for algebraic. Can you see what I'm typing?
I think now it's being hidden by this thing for some reason. Yeah.
Algebraic. It's too small, right?
Yeah. I think if you write with the pad.
Okay, let's move to the pad. So error is
There you go.
Is algebraic intermediate representation. Okay, it will be an algebraic representation of a statement, and we will see in a moment what kind of a statement. So I guess people following the Start at Home sessions are familiar a bit with errors and will be a bit familiar with what I'm about to describe. For those who are not familiar, I'm not assuming anything like this. So in the error statement, what we have, it's a constraint satisfaction problem that assumes some input, which is, when we talk about proof system, it's kind of a private input, which we can think of as a very long tape, having a lot of elements. One could imagine a Turing machine, for example, and a circuit. So we have some circuit, it has several inputs, and an output. Okay, so in contrast to other proof systems, for example, SNARKs, where there is a circuit as well, the number of inputs to the SNARK circuit is just as the entire input. Here we have much less inputs to the circuit than the actual witness or the input or the tape. What the error statement checks is the following. It takes as input an area of the tape and verifies that it satisfies the circuit. And what it does again, it just moves this circuit then, for example, to another area and check this as well. Okay? And does it again and again and again and again. And we would say that the tape satisfies the circuit if for every such batch of inputs, the circuit is satisfied. This is in high level, this is in the bird's eye to understand what kind of problem are we handling here. So it is, what kind of problems can we describe in such a way? So it is really very relevant to the discussion that we are about to have. You can think about the tape as something that contains an encoding of, for example, CPU registers, and the circuit as something which is satisfied by taking two states of CPU registers and verifies that the second state really is the next step for the previous state. So this way, we can say that the circuit verifies that the tape encodes a good trace, a real trace of execution over this CPU architecture. Why is it algebraic? It is algebraic because, first of all, the reason it is algebraic is because this is the way Stark works. This is the way most of the proof systems work. They require some algebraic input. And in this specific case, the elements of the tape are field elements of some finite field. And the circuit is actually described as a multivariate polynomial over the same field. So this is the kind of problems that we want to deal with. You can, if you're familiar with the arithmetization techniques, you know that you can take any Boolean circuit and encode it as a multivariate polynomial over a finite field, and this would be non-optimal result. And a lot of the challenges of writing a good error or designing a good error is how to build this circuit to be as close to optimal as possible. Now, if we take a step back and we think of how we use this information when we think about proof systems, the circuit, just like, for example, the CPU architecture, is something that should be known to everybody. It is known to the verifier, for example. And the tape, which is like the execution trace, is known only to the prover, and the prover proves to the verifier they know a real trace, execution trace of some program. For example, there could be some boundary constraints that I did not get into that show that we start from some specific program. This is in high level an error. If there are any questions, I'll be happy to answer.
Let's see. So if there are questions, please use the ask a question. Okay. Yeah, go ahead.
Will it be possible to interrupt error between error and other
intermediate representation?
Intermediate representation, like LLVM intermediate representation or Ethereum Yule? I'm not familiar with Ethereum's Yule. I am familiar with LLVM. So LLVM is an intermediate representation that built and designed to both efficiently be executed over a CPU like Intel, AMD, a very standard CPU architecture, and to take code, for example, you can compile from C++ to LLVM. This is the design goal of LLVM. The design goal of algebraic intermediate representation is to be efficiently proven or efficiently verified, and there is a very different cost model in this case. So, for example, there is the question of what is the complexity of the circuit, of the polynomial. What is the degree of this polynomial? The degree of the polynomial is very important. And it's actually, I said it's a single polynomial. Actually, when we design Earth, we're not bounded to use a single polynomial. We can split it to several polynomials, and we usually do this in order to reduce the degree. So there are many different cost models. Another factor is the size of the field. So there are many different cost models which differ a lot from standard architecture. So the design goals of Earth is very different from LLVM or other things that should run over Intel architecture.
I want to add to that. Unless, do you want to add to that? No. Okay, I want to add to that. Wait, first of all, a request. Please, it's much better if you use the ask a question. I'll just give you an example. You go to the ask a question and you say, I have a question. And then it's easier, and then people can vote on it.
I see it. So I see a question here about the LLVM, which is built to be independent of the hardware. I agree with this. Okay, but it still has some assumptions. Yes, you want to say something about this?
It assumes that it runs over a CPU.
Mm-hmm.
So instructions are executed one after the other and so on, which is not the case in algebraic intermediate representations. For example, I don't know if it assumes anything about the integer type, the primitive type, but if it does, then also this will be
I want to add that okay, you can definitely once you have a universal language or machine, and we'll get to that. We're sort of jumping ahead to the universal world.
Yeah.
You can, of course, that's the definition of universal. You can simulate with it. That's the definition of a universal machine. It's one that simulates any other machine. The interest, so the like a high level answer is yes. Any other architecture can be simulated by any architecture that is Turing complete. The interesting question, I mean, there are two practical questions. One is that of efficiency, and the other is just the more prosaic, but often the blocking question of, is it in the plans of writing this, and will someone write it, and when? And here I think what both Michael and Yoel are saying are that likely it's not the first thing to come because it's not the most efficient and wanted, but...
No, I was just referring to the fact that it's not immediate. So you have to add a few levels of abstractions before you go from an R to something like LLVM.
Just to give the feeling of the difference here, in most of the architecture, CPU architectures we're familiar with, bit operations are considered probably the cheapest operations you can do. This is something, if you can do it with bitwise, cyclic shift, things like that, bitwise XOR, this is very cheap. When you go to the algebraic world and your constraints are actually polynomials, bit operations are horrible. This is very hard to do efficiently. Or on the other side, when you go to the algebraic world, it is very easy to do a modular arithmetic. It's very easy to do modular addition, modular multiplication in the field, of course. But of course, when you go to a standard CPU, this requires some non-trivial additional computation, and this is not the native language of such a CPU.
Yeah, but as Eli mentioned before, all of this is possible once you have a universal machine.
Okay, now, so again, I want to remind everyone, please use the ask a question. It's easier to read than
there is a question.
No, it was I wrote the question, which is, and then we can start answering and done answering. So please use the ask a question. So now, okay, the very first, any one of you who has tried using any kind of proof system, probably the very first thing you did is some sort of hello world, and you wrote constraints by hand for something. So you are basically doing the analog of ASICs. And so now I want to hand it over to Lior to say a little bit about how we sort of dealt with building, because, by the time we moved to something like Cairo, we have been already constructing very complicated airs in our case, so very complicated circuits that deal with, both cryptography, things like whatever, Petersons and signatures, and also logic. So there were quite the circuit that Michael was describing became very, very complicated. And, there's only so much that the human brain can capture. So, Leo, please, walk us through how we dealt with this. And I guess I should I'm going to mute myself and, no, wait.
No, don't mute yourself.
Okay, but I'm going to allow,
But I will show the visualizer.
Okay, so I'm going to focus.
In a few minutes, so you can keep it as is.
Okay, so now I'm going to just enlarge this. Okay,
okay, so we started by doing the ASIC version of writing errors, which means basically write them by hand. The reason was that we felt that this is the most the most efficient thing we can do, and it wasn't clear that any of the other methods, such as DSL or simulating a CPU or anything of these approaches will be efficient enough for what we need. So we started with this, and to do this, okay, so this is similar to this building this circuit that Michael described is similar to designing an ASIC. You have to basically decide where do you want to put your transistors, where the transistors are field elements. Michael didn't mention it, but the air is not one-dimensional. Actually, you have 2 dimensions. It's a table of field elements, usually with a small number of columns, and you have to be smart about the way you order the field elements there. So what we did was we've built a Python library in which we can describe the circuit, the list of polynomials. So sorry. So we are still in the phase that we are specifically writing all the polynomials that are going to be present in the circuit, but we are doing it using a Python infrastructure, which allows us to write components that can be composed in various ways, and sophisticated placement, and together with this, we built a nice visualizing utility that I want to show. So now I will share my screen.
Okay. No, I think you need to share your screen.
Okay, so can you see my screen?
Just 1 second.
Yes.
Okay, so so this is an example of an air. This is the air that we are using in Vidu, our VDF system, and you can see this is the table that I mentioned. Every cell here represents a field element, and every gray rectangle represents a constraint, a polynomial. So, for example, I don't know if you can see or it's too small.
It's very hard to see.
Okay, so it says, I'll just say what's written here. It says x minus a cubed, and a is somewhere to the right outside of the. Or maybe it's not a. Let's take a simpler example, which is the Fibonacci, an air for the Fibonacci sequence. So basically, you have 2 columns, x and y, and you have constraints such as the first element in the Fibonacci sequence must be 1, and the step of the Fibonacci sequence, which says that the new Fibonacci element is the sum of the previous 2. And using this, we could look visually on the airs that we've built, and we actually did some.
Wait, can we just stay with this? I have a question. This is a clarification question. Michael spoke earlier about this sort of infinite long stream and then the small circuit. So I guess what we're seeing here now is
first it's transposed. So what Michael said, draw as the
row
as a row is now a column, and actually you have a few columns.
Okay, so you have like a few tapes, and what we're seeing now is not the full tapes, right? It is so what we're seeing on the screen.
This is a Fibonacci, a very short one. This is a longer one.
Okay.
And
how do we know? So Michael spoke about a small circuit that is applied every time to.
The fact that you can see that it says step, step, step here. It's always the same constraint applied every time on different cells, but it's the same constraint and the same ordered in the same way. So this and yeah. And for example, this constraint says that you take the last element and copy it to the next line, and also it repeats across all the rows.
And the step is actually the Fibonacci formula?
And the step is the Fibonacci formula, yes. X equals A plus B.
Mm-hmm.
So I will show more complicated errors. For example, this is an error for verifying an ECDSA signature. So it's more complicated, as you can see, but you can actually look at the constraints and make sure that it does what it should. Okay, so we've built, using this approach, we've built our first product, which is StarkX, Stark Exchange, and diversifies operating an exchange based on this error that was built in this way.
So I mean, I guess also the listeners can see here that, I mean, this is a pretty complicated, right? This is a pretty complicated, you know, circuit or thing to think about. So how, like, and this of course leads to the need for some further automation that we'll get to in a minute. But like, how does one think, or, you know, how does one, let's say you want to write StarkX or you want to write the Peterson commitment or something, how do you go about, even if you have a visualizer, I mean, are you working with a visualizer? Are you writing things in Python? How does it get?
So the most important thing here is to work with abstractions and to work with components that create more and more complicated layers. So there are things that are very, very simple, like an error that checks that a number is between 0 and some power of 2. And there are more complicated things, like an error that computes the sum of points on an elliptic curve, since elliptic curve is just simple, is an algebraic object, so this is still a very easy to build error, and then you continue from there. So you can build the ECDSA component based on a component that adds points on an elliptic curve, and then you can build DEX that uses the ECDSA and Peterson, and you have a component for Merkle tree, and so on.
Okay, so we have 2 questions. If you can also open the questions, I'll read the first one and you'll answer it. This one is coming from Harish, who I think we know. Hi, Harish. The A and the B, Harish is one of our board members. I mean, there may be some other Harish that is joining, but I'm guessing it may be him. One of the board members of Starkware is Harish. Hi. So the A and the B in the constraints, where does the prover read those from, and how does it know where to read? How does it know where to read from? Are those register names? Do you want to open again so we can see it? Maybe it will be clear.
Okay, so
yes, I will open it again. Wait, let's focus on your screen, and now you're going to share, right?
yes. Okay. So
wait. We need to see it. Just 1 second. Just 1 second.
Fibonacci example.
Yeah.
Okay. Great. So the question was about the A and the B here, and the answer is that it's all you see is a visualization of what Michael described before. So the constraint itself says something like this. You have to apply. The constraint comes with a domain, which is in the case of the step constraint. The domain is all the rows except for the first one, and a polynomial over a few trace cells. Each trace cell is a number of columns. So this is like the first column. So this B here is the first column in 1 row above the origin row, and the A is the second column in the same row, and the X, which is the cell I'm on, is the second column of this row. And then, so this is the information that constitute the constraint, and then and this is the constraint that actually goes into the proof system. What you see here, the names A and B are automatically generated by this visualization utility, and it's not part of the actual error. It's just a way to visualize it. I hope this.
I want to add something that the way that both, maybe you still want to share the screen, the way that both the verifier and the prover actually discuss, cells of the tape that Michael described, that we often call the trace. They refer to them algebraically. So the cells themselves are being indexed by elements in a finite field, and then sort of you index them by doing, either +1 or, something like that within the field. So at the end of the day, everything is going to live in a very algebraic world over finite fields, and everything, so there's no A and B, there are only like field elements and so on. But yeah, so this comes from...
So actually I want to add to that, that an error is just one abstraction between the high-level specification and the proof at the end. So you can take an error and apply to it the Stark protocol and get a proof. And I'm sure that there are other protocols that get an error as an input and will generate another proof. So all the questions of the form, how does the prover or verifier knows those values are not part of the description of the error, but part of the description of the Stark protocol that takes this error and generates a proof from it.
Okay. Next question by Yaakov M. Is there a programmatic way to be assured that the constraints that are produced correctly describe the language you prove membership of? That's a terrific question. Mm-hmm. By the way, just I want to say, if Shachar wants to, Shachar's gonna go up next. But if if you like anyone who wants that, Shachar, do you want to answer this?
Sure, I can answer this. Well, we have some sorts of tests we use to programmatically check what is for example, if we constrain the prime to be some small prime, we can go over all the possibilities that satisfy this error and check that this is indeed what we want. This is just one type of tests we have. This is a soundness test. Other methods there are possible to use are just to provide a mathematical proof of this error, which is semi-programmatic, I think. It can be verified programmatically, but still it's a mathematical proof that this indeed the only verifiable things are what we want. So this is the things we use.
Do you want to add?
No.
Okay. So we have the last question. ECDSA involves a hash function. Does the error encode that hash function as well? And isn't that very complex? This is coming from Alan.
Yeah, this is a good question. Yes. Okay, so the ECDSA component that I showed does not include the hash, the part of hashing the message. In order to hash the message, we use the Peterson hash, which is another component. And since the Peterson hash is based on elliptic curve computations, it is doable in errors in a very efficient way.
Okay, so the next part is going to be, and I see I'm going to jump out because I see I need the battery here. So just in a minute, I think there's probably lest this gets shut down. So now I'm going to basically hand it over to Shachar to sort of discuss the following things. Okay, so Lior described how we sort of hand wrote a bunch of constraints, and of course this gets complicated. What are the options in the next step, right? Is it, should it be a DSL, a domain-specific language with some limited functionality? Should it be a general purpose computer? And if so, then we'll talk a little bit about the pros and cons of Harvard versus von Neumann and why we chose von Neumann. So yeah, please, Shafan, take it from me.
Okay. Hi. Did I just share the screen? No, I can't share the screen, apparently. Well, no matter. So I think the analogy
I can share your screen if you want to share it.
I can share it now. Let's see. I'll share it. Okay. This is
wait. So now wait just 1 second. I'm going to share it as well. Okay, go ahead.
Okay, same thing in black. Okay, so the analogy we had in the beginning that errors are like ASICs is a good one, I think. The tools we developed over the time give us very good abstractions over the way we create the errors. We don't have to think about exactly where the trace cells sit on, or how to squeeze them together to get efficient things, or the domains we talked about earlier of the constraints. We don't really have to mess with these small details. So this is already a good step above the simple handwriting errors. The next step that we considered was using some sort of a DSL. For example, when you develop ASICs, I imagine there are some tools like Verilog or VHDL that has some language to them and give people better tools to build ASICs. Well, we considered using some DSLs, but ultimately we decided not to. First of all, we felt that our framework was very, very good. Python allowed us a very good flexibility in how we apply it and even the way we test it. And building a DSL over it wouldn't have given us a lot of benefit. It would have made our building process less flexible, and it required some development time, obviously. So even though we considered it for a while, we decided ultimately not to go to the path of DSLs to create ASICs. The next step we thought about is, well, we did want to make it very easy to write errors or something we can use for Stark proofs. We wanted to be a lot flexible than what we can achieve even with DSLs. One is basically something closer to Turing complete, something that looks and acts like a program, a simple program you would write in the computer. So we started working on it. I think we had a lot of thoughts like a year and a half ago. I think it started. Over the time, we had a lot of ideas. Now, the main challenges we have there are that this architecture is very, very different than modern hardware. Like, for example, everything is algebraic, like Michael said before. We don't have cheap bit operations. We don't have easy addition of an integers modulo 2 to the n. The memory management is a lot less obvious. For example, in your modern CPU, You can allocate memory. You can free memory if you don't use it anymore. In errors, it doesn't really work that way. We have this one big trace that is the trace of the program. There is no meaning to freeing memory on this thing. So there are a lot of considerations that went into it and different ideas. But ultimately, I think we found something that is quite efficient, and efficiency is the key here. We could have taken other approaches that were had a lot of benefits, like someone mentioned. Maybe use LLVM and try to make something that works for that, or maybe EVM, or just complying x86. These are some ideas that came up during the thought process. But we decided we wanted something efficient. Like one of the benefits of Stark is that it is efficient, and we want to capitalize on this and make something that will be also easy to write and will give a very nice performance and results. So even though it is possible, like I said, compiling other stuff, it's a lot less efficient.
Shahar, I wanted to ask, you talk about efficiency. What does efficiency mean here?
Yeah, it's a good question. The main metric for efficiency we use is the size of the trace. This big table you saw before, it has a number of cells, and in the end, the Stark proofs are quasi-linear in the size of this trace. So if you use a lot of trace cells, if you waste trace cells, if you have unused things, it's going to cost more proving time and a bit more proof length. So trace length is one of the major things. Of course, we can't expect to get the efficiency of handwritten errors, because they're handwritten and very efficient, but we want something not a lot worse. Well, the thing I'm describing here is that is the next step after DSL is some sort of a universal machine in air. So the idea is to have just one specific air with very specific constraints in the circuit, that this air can simulate every program in some instruction set. There are a lot of benefits to having just this single air, other than being able to write things in a higher level programming language and compiling them to this instruction set. Having just one error means it is easier to audit this error. Not every application that goes out, we have a different error, and then people need to look at the equations and see if it's good. With just a single error, it is enough to be assured that it is a good error like one time. And other than that, every program using it, we can just look and check the program, the code, and it's a lot easier to check code than it is to check polynomial constraints. Yeah.
I have some sort of guiding questions, and also Michael had a question that you want. Michael, do you want to wait? I'll add video back here. But Shahar, if we interrupted you and you wanted to say a few more things, and then we will sort of add the questions, let me know.
Well, you can ask questions. I have stuff to say like a lot, but if you have guided questions, go ahead.
Michael, go.
Just wanted to ask, you mentioned that when we do errors, handcrafted errors, it is more efficient. So when we do it in a high-level language, is it only loose, or can we get some efficiency gains as well?
Yeah, I understand why you're asking that. Well, historically, when we moved our product in Stark Exchange, the first version is using like these handwritten errors, and the second version does use Cairo. We actually gained efficiency. It was more efficient than the previous one. The main reason is that using high-level languages lets you apply optimizations a lot easier. Uh, for example, one of the things we had to uh, incorporate in the handwritten Stark is that we have different kinds of transactions in Stock Exchange. Like one type of exchange is a settlement, and it has 4 changes in it. And we have another kind of transaction, which is a transfer, which has half as much changes. Uh, but we had to allocate in the air, in these boxes you saw, enough trace cells to handle settlement. So when we used them for transfer, we had wasted trace cells that were not used. Uh, this, of course, doesn't apply when we have this universal machine because it's just code. Each block is just a simulation of an instruction. So if the settlement has 1,000 instructions and the transfer has 500 instructions, it will take half as much trace space, which is a saving. Other optimizations we used are the in the Merkle update part. The heaviest computation, I would say, in the air of a Stark Exchange is the Merkle updates. We have the Merkle tree, and every time we do a change, we have to prove the Merkle authentication path of this change on the Merkle root. And in the single air, what we just did is every transaction, we just did the simplest thing and provided all the hashes we had to provide it for the entire height of the tree. But when we moved to the code version, to the universal machine in Cairo, we could do it's a known Merkle update optimizations. When you have a lot of updates, when they want to apply them together at once, you can save a lot of hashes, especially at the top of the tree. So we used that, and this saved a lot of hashes, which is the main cost factor of this proof. So our proofs are a lot cheaper, even though theoretically it's supposed to be slower. It lets us do a lot of more complicated things because code is easier.
So I have a question. When you, in terms of the error that would arise, okay, if you had something that is a DSL, a domain specific language, versus Harvard architecture versus a von Neumann architecture, how would the transition from programs to errors and starks look in each one of these 3 branches? Like, what would be different between, DSL, Harvard, and I'm asking also those here, but Shahal, maybe you want to go first, or?
Yeah. Well, first of all, in how you write this code, allegedly, when you write a DSL, you're very much restricted. For example, you can't do some Turing complete things like unbounded loops or recursion. It just it doesn't translate well to this error constraints. Uh, Also, things that can happen is if you have a conditional branch, for example, then if you take the path that does less instructions or less code in the DSL, it won't actually save trace cells because we need to allocate things for the other branch as well. So it's really restrictive, and some things are not as efficient. When we go to the Harvard architecture, which is actually is like a programming languages, but the difference between the Harvard and the von Neumann is that the code is predefined in its own code segment, part of the memory, if you will. It doesn't let you do some maybe cool things, some things we even use today. For example, things we use and is some sort of a guessing the program and just comparing its hash. Because in von Neumann we can write just instructions in memory and then jump to them and run them, and this lets us do some efficient things, some very cool things. And Harvard, you just can do that. The reason to use Harvard sometimes is perhaps it has a more efficient implementation, perhaps it's easier to write, but in our case it just didn't seem like it was easier in any way.
And I want to add about the von Neumann architecture that another advantage is that the number of constraints, actually the error, is independent of the program in the von Neumann architecture. In the Harvard architecture, you can have an error that contains the specific program, and the fact that the error is independent of the program has at least two advantages. One is that you have a very small number of constraints. If it's independent of the program, then it doesn't matter how long the program is, the number of constraints is still the same. And the second advantage is more practical. It's much easier to maintain only one verifier, for example, on the blockchain, if we're talking about the blockchain, and easier to audit and so on.
Okay, Michael, do you want to add? Okay, our time is nearly up. So first of all, if you have questions, please use the Ask a Question. I guess I want to ask this sort of free-form question. We have stuff written by DSLs. Sorry, not by DSLs. In hand, the ASIC model. Now we at Starkware are starting to deploy things with Cairo, which is, you can think of it, I mean, if you go to CPUs, maybe it would have been like the algebraic analog of, I don't know if x86 was the first chip, or maybe there was some previous, some prior chip that was very limited. So where do you think, okay, first we're going to take the question that is there, but you can think there are a bunch of questions. But meanwhile, you can think about this question, where, if you have to sort of guess, 2 years or 5 years in the horizon, what kind of sort of algebraic CPU will we have? What will be the differences? What would you want them to do? Okay, so but first let's ask the questions and answer the questions, and then we can go back to this. So the first question by Patrick: doesn't a longer program still result in a longer trace, though?
So not necessarily. The main thing that determines the size of the trace is the length of the execution. So you can have a very short program with a loop that runs a lot of times, and you will get a very long trace. But it is bounded from below by the length. The size of the trace is bounded from below by the size of the program. This is true. But we still have, the effect of the size of the trace on the running time of the verifier, for example, on the proof length is polylogarithmic. So actually relatively constant for practical needs.
And you wanted, I think, to say that in the Harvard architecture, if you embed the entire program into the constraint system, the verifier is linear in the constraint system.
Yes.
So if the program is very complex, then the verifier complexity would become higher.
Yes.
Good point. So you're saying, sorry, in Harvard architecture, bigger program means verifier running time is at least linear in that because sort of it needs to know the constraints. Whereas in von Neumann, it's only logarithmic because this is just part of the memory or data, and there's a very, okay,
Yes.
Thanks. Okay, next question. Will Cairo include some form of formal verification support, pre and post conditions, etc.? Shoaib is asking.
So it doesn't include any such formal verification support at the moment. I don't know about the future.
I'll add to that that's something we would like to happen, but yeah. Next question. How do you implement memory? Is it based on the P-lookup construction? So this is by Dan Krad.
You want to answer it?
I'm not familiar with the field.
It's not based on this. Do you want to answer what it's based on?
Please go.
So it's similar. It's similar to the way I think Plonk is using it, and probably also P-lookup.
It goes back to Bootel and maybe Groth.
Yeah, I don't remember the exact paper. It was
The permutation.
Yeah, but it's based on a permutation trick.
Yes, permutation technique. That appeared. So if the P-lookup construction uses the permutation, which I think goes back to, I think it's Bootel and Groth, but I'm not entirely sure. So it's that technique.
Maybe just to add some more details, I guess Dan Krad is familiar with proof systems because of this question, but maybe not everybody here familiar with what is difficult about memory. If you remember, in the example that I showed in the beginning, I said that the tape could contain values of registers, and every time what the circuit does is verifies a previous set of registers, and the next set of registers is consistent. But what would happen if, for example, the registers say that the next instruction to run is to load information from memory? How can we know? And for example, 1,000 instructions before that, we stored something to the same address in the memory. How can we know that we read something which is consistent with what we stored before? So this is what Lior mentioned. There is a trick of permutation, doing permutation over this trace, over this tape, that allows to run another circuit or something very similar on the permuted trace, and to check that whenever we load something from memory, it is consistent with the last thing we stored in the same cell.
Yeah, so I want to add that the constraints that you can easily write in as are in some sense local. So every constraint deals with only cells in the local environment. And what we need for memory support is exactly this global thing, which is not part of the most basic Stark protocol, but some enhancement of the protocol.
Okay, next question that goes to Shachar, because I think he spoke about it. Can you clarify the statement on conditional branching in DSLs? You mentioned encoding both branches with the DSL. Is it not needed for air?
Well, DSLs are also for air. It is not needed in the universal machine model. If you use DSL in simple air, then you still need the cells for the path not taken, and then just in the end choose if you take the result from this one or this one. But in a universal machine, you just have instructions. If the instruction says go to this space, not this one, you'll just have the instruction that actually run, not the one that didn't run.
Okay. Thank you. So now I want to ask the last question, and again, if there are more questions, you're welcome to add them. So, like, what's missing now, and what would you like to see added to Cairo? Some future version of a universal machine? Like, what would you like? So maybe let's Michael, Leo, Shachar. If you want not to answer the question, that's fine. Okay, so go ahead. Wait, I'll just enlarge the screen so we see.
So the question is, what would we like to see added to Cairo?
Yeah, like, what's behind the horizon? What's coming after that, or what would you like, in 2 years or 5 years?
So, as mentioned in one of the questions, I think because Cairo is planned to be used as in a very delicate area, so some utilities for formal verification around this would be a very good utility.
If I can add, I think there is a room for Cairo to grow. For example, it can be a bit more efficient than today. Not a lot, but there is place to make it even more efficient than it is today. And also, what I want to happen is for people to have the ability to interrupt with other things like the EVM, which is not exactly something for Cairo, but it can be a lot of tooling around Cairo and on top of Cairo, maybe compiling from higher level languages, which I think can be done. If you like functional programming, then it's very, very suitable for Cairo, so you can think about that. And last thing I can think about now is to allow users to add some custom errors along their side. So if they want to have like the general business logic of the application in just regular programming language, but not lose the benefit of handwritten errors for the low-level recurring parts. So they will have the ability to incorporate both of these.
Leo, do you want to address the question?
So I think maybe compilers from many higher-level languages. LLVM can be one example.
Okay, so I see there are no more questions. So I want to thank very much my colleagues and the speakers on this episode. Michael Ryabtsev, co-founder and chief architect; Leo Goldberg, head of algebra research; Shachar Papini, engineer. Yeah, thank you very much for attending, and see you again in roughly 3 weeks. Good night, everyone, or good morning, or whatever place on the globe you are. Thank you.